Alright, let's tackle the subsets problem, generating the entire power set of an array. So if you have 1, 2, 3, you need every possible combination, empty set, single elements, pairs, and the full array. Here's the key insight: at every element, you have exactly two choices, include it or don't. That decision tree? That's backtracking. We're gonna build subsets incrementally and explore every branch of possibilities. Super simple start, we create an empty list called result that's gonna collect every single subset we generate. By the end of execution, this thing will hold 2 to the n subsets, where n is the length of our input array. That's the power set, baby. Here's where the magic lies. We define a nested function called backtrack that takes 2 parameters. The start index tells us where to begin picking elements from, so we don't create duplicates by going backwards. And current is the subset we're actively building up. Think of start as a bookmark. It says, hey, only look at elements from here forward. This is the line that makes this problem different from something like permutations. We append a copy of current to our result at every recursive call, not just at leaf nodes. That means the empty list gets added, partial subsets get added, everything. Every single state of current is a valid subset. We use current, smiley face, to make a copy because current is gonna keep changing as we backtrack. Now watch what happens. We loop from start to the end of the array. For each index I, we append nums, I, to our current subset. This is us saying yes, I'm including this element. The fact that we start at start and not 0 is crucial. It prevents us from ever picking an earlier element again, which would give us duplicate subsets in different orders. And this is the key insight for avoiding duplicates. When we recurse, we pass I plus 1 as the new start position. Not start plus 1, but I plus 1. This means after picking element at index I, we can only pick elements that come after it in the array. It's like a one-way door, you can only move forward, never back. This guarantees every subset is generated exactly once. Here's the classic backtracking move: we pop the last element off current. This undoes our choice so we can try the next option in the loop. Think of it like hiking: you walk down one path, hit the end, then walk back to the fork and try the next trail. Without this pop, our current list would just keep growing and we'd never explore alternative subsets. Finally, we start the whole process by calling backtrack with index 0 and an empty list. Start at the beginning, with nothing selected yet. From there, the recursion tree fans out and explores every possible include or exclude decision. Once it's all done, we return our result list containing every subset. Time complexity is O of n times 2 to the n. There are 2 to the n subsets and we spend O of n copying each one. Space complexity is the same for storing all subsets, plus O of n for the recursion stack. Here's your takeaway: in subset generation, every node in the recursion tree is a valid answer, not just the leaves. That one line where we append at the top of backtrack? That's the whole difference between subsets and other backtracking problems. Beautiful, right?